Welcome everyone to AI Forward, the podcast where we bridge the gap between cutting-edge technology and business strategy. Today, we're diving deep into a topic that's absolutely fundamental to making AI truly intelligent: memory. We often hear about large language models, or LLMs, but how do they remember? How do they learn, adapt, and maintain context over time? It's more complex than you might think, and frankly, it's evolving incredibly fast. To help us unpack this, I've got a fantastic panel of experts today, a mix of deep technical minds and sharp business strategists. Welcome, everyone.
Thrilled to be here. This is a topic close to my heart, or should I say, close to my AI's hippocampus.
Ha, good one, expert one. Yeah, it feels like we're finally moving past the goldfish memory phase of AI, doesn't it?
Absolutely. So let's set the stage. Why this sudden explosion of focus on AI memory? Expert 3, maybe you can kick us off from a technical perspective.
Well, it's driven by the sheer scale and capability of modern LLMs. Early AI had memory, sure, but it was often brittle or task-specific. Now, with models interacting over longer periods, handling diverse tasks, and needing personalization, robust, dynamic memory isn't just nice to have, it's essential. Without it, LLMs are essentially brilliant systems with severe amnesia.
And from a business angle, that amnesia is costly. Imagine a customer support bot that forgets the conversation history mid-chat, or a personalized recommendation engine that treats you like a new user every single time. That's not just bad user experience. It's lost revenue, lost efficiency, and frankly, lost trust.
Excellent points. The context paper we're drawing from today proposes a really useful taxonomy to understand the different kinds of memory in AI. Expert 5, can you break down these categories? Parametric, contextual unstructured, and contextual structured.
Sure, think of it like different ways we store information. Parametric memory is the knowledge baked into the model's parameters during training, like skills learned so well they become instinct. It's fast, always there, but hard to update precisely. Think general world knowledge. Then there's contextual memory, which is more explicit, like notes you keep handy. Unstructured is like a messy scrapbook, raw text, images, audio clips from interactions. It's flexible but can be hard to search efficiently. This includes recent chat history or sensor data. Contextual structured memory, on the other hand, is like a meticulously organized filing cabinet or database, knowledge graphs, tables, ontologies. It's precise, easy to query, great for symbolic reasoning, but requires effort to set up and maintain.
Filing cabinets and scrapbooks. I like those analogies. Expert 6, as a business leader, why should you care about these distinctions? Does it change how you approach building or buying AI solutions?
Oh, absolutely. It's fundamental to strategy. Knowing these types helps you ask the right questions. Do we need an AI that relies on its pre-trained instincts, parametric, or one that learns continuously from specific interactions, contextual? If contextual, do we need the precision of structured data or the flexibility of unstructured? This impacts cost, scalability, maintainability, and crucially, adaptability. A system heavy on parametric memory might be cheaper initially but harder to update with proprietary company knowledge. A system relying on complex structured memory might be powerful but require significant data engineering investment. It's about matching the memory type to the business need and understanding the trade-offs. It's not one size fits all.
Understanding the what is crucial. Now let's talk about the how. The paper outlines 6 core memory operations. Expert 1, can you walk us through these atomic actions?
Happy to, they really capture the life cycle of memory. We have 4 for management. First, consolidation, which is like how our brain turns short-term experiences into long-term memories, maybe summarizing interaction logs into a persistent store. Second, indexing. This is vital for actually finding stored information later. It's like creating an index for a book, adding tags or pointers, whether symbolic or embedding based, so you don't have to read the whole book every time. Third, updating. Memory isn't static. This involves modifying existing memories, correcting facts, adding new info, refining understanding. Think editing a specific entry in your knowledge base or even subtly tweaking model parameters. And fourth, forgetting. This sounds negative, but it's crucial. You need to remove outdated, irrelevant, or even harmful information. Think GDPR right to be forgotten, or just pruning old logs to save space and reduce noise.
And the other two operations are for utilization, retrieval, which is the act of pulling the relevant memory out when needed, based on the current context or query. This is the heart of RAG, or retrieval augmented generation, but it applies more broadly. And finally, compression. Especially with long contexts or vast memory stores, you need to shrink the information down, keeping the essentials while discarding fluff, either before it goes into the model or after retrieval. It's about efficiency for both processing and storage.
Consolidation, indexing, updating, forgetting, retrieval, compression. It sounds like a complete toolkit for managing information. Expert 7. How do these operations translate into tangible business advantages or challenges?
They directly map to capabilities. Consolidation and updating enable systems that learn and adapt over time, crucial for personalization. Indexing and retrieval determine how quickly and accurately the AI can access relevant knowledge, impacting response times and quality in customer service or expert systems. Forgetting is huge for compliance and privacy, as Expert 1 mentioned, but also for relevance. You don't want your AI assistant stuck on preferences from 5 years ago. And compression, well, that hits the bottom line directly. Processing less data means faster inference and lower compute costs. It's the 80-20 rule in action. Find the critical 20% of the memory needed for the task.
That cost aspect of compression is often overlooked. Let's pivot to how these operations combine in real-world systems. The paper highlights 4 key research topics. First up, long-term memory. Expert 3, what are the big challenges and breakthroughs here?
Technically, the challenges are immense. How do you effectively index potentially vast histories spanning multiple sessions? How do you retrieve information that's not just semantically similar, but temporally relevant or causally linked? Systems like Hipparag building graph structures or theanine using temporal links are fascinating steps. Consolidation is also tricky. Simple summarization loses detail. We're seeing more sophisticated methods like MyAgent modeling memory strength over time, trying to mimic human memory dynamics. And then there's personalization, encoding user preferences without constant retraining, which brings us to techniques like parameter-efficient fine-tuning or dynamic memory augmentation.
Expert 4, from a strategic view, what's the killer app for long-term memory?
Personalization is definitely a huge one. Think truly adaptive learning platforms, healthcare companions that remember patient history accurately, or financial advisors that understand your long-term goals. It moves AI from a transactional tool to a relational partner. Another area is complex task completion over time. Autonomous agents performing multi-step research or project management need to remember plans, progress, and learnings across days or weeks. Long-term memory is the foundation for that level of sophisticated agency. It builds loyalty and deepens engagement.
And it's not just about remembering facts, but relationships and context. Think multi-session customer support where the agent remembers the entire history, not just the last 5 minutes. That avoids customer frustration and leads to faster resolution.
Okay, next topic, long context memory. This feels very relevant with models boasting million-token context windows. Expert 2, what's the memory angle here?
It's twofold. First, parametric efficiency. Handling those massive contexts means gigantic key-value or KV caches, essentially the model's short-term working memory during generation, storing all that is incredibly memory-intensive and slow. So we see techniques like KV cache dropping, selectively discarding parts of the cache, like H2O keeping heavy hitters or streaming LLM using smart eviction, or optimization methods like quantization, KV quant, KIVI, or compression, less to shrink the cache footprint. It's a constant trade-off, save memory versus potentially losing information.
And the second part.
Contextual utilization. Just because a model can read a million tokens doesn't mean it understands them equally well. There's this fascinating, lost in the middle problem, where models tend to recall info at the beginning or end of a long context better than the stuff buried in the middle. So techniques focus on helping the model find the needle in the haystack. This involves smarter context retrieval within that long window, maybe using graph structures, graph reader, or fragment-level selection sparse RAG, or context compression before feeding it to the LLM, like long LLM lingua or RECOMP summarizing relevant chunks.
It's like giving the AI better reading glasses and speed reading techniques for that massive novel. Expert 6. What are the business implications of mastering long context?
It unlocks entirely new applications. Analyzing lengthy legal documents, summarizing extensive research papers, generating code based on large existing code bases, querying entire company knowledge bases in one go, these become feasible. But the efficiency part Expert 2 mentioned is critical. Million-token contexts are expensive. Businesses need solutions that are not just capable but also cost-effective. Innovations in KV cache management and context compression directly impact the ROI of deploying these powerful models. It's about making massive scale practical.
Moving on to a really intriguing area, parametric memory modification. We talked about parametric memory being baked in. Expert 5. How are researchers trying to change that?
This is about surgically altering the knowledge stored within the model's weights without full retraining. Three main flavors: editing, unlearning, and continual learning. Editing is like correcting a single fact in the AI's brain. Techniques like ROAM or MEMIT try to locate the neurons responsible for a specific fact and then precisely modify their weights. Meta-learning approaches MEND, KE train a separate editor network to predict these changes. Others use prompts, IKE, or add small, dedicated modules, ColliNet, WISE to override or adjust behavior without touching the core weights. Unlearning is the flip side, selectively removing information. This is critical for privacy or removing biased, harmful content. Again, you see locating then unlearning methods, WAGLE, prompt-based approaches, ICUL, adding specific unlearning layers, EUL, or modifying the training objective itself. And continual learning is about incrementally adding new knowledge over time without catastrophically forgetting the old. This involves regularization techniques, constraining weight changes for important old knowledge, or replay-based methods, mixing old data or generated pseudodata with new data during updates.
This feels like we're moving towards AI that can truly adapt and evolve its core knowledge. Expert 7. Strategically, why is this area so important?
Adaptability and maintenance. Businesses need AI that reflects current reality. Editing allows for rapid updates, correcting misinformation, adding new product details. Unlearning is essential for compliance, safety, and managing data privacy mandates like GDPR. It's about control. Continual learning promises systems that improve over their lifetime, learning from new data streams without costly full retrains. Think of AI agents in dynamic environments like robotics or autonomous systems needing to constantly update their world model. This is fundamental for long-term relevance and reducing operational overhead.
But I'll offer a slightly contrarian view here on unlearning. While the goal is laudable, achieving provable, complete unlearning from deep within a complex neural network is, well, incredibly difficult. Are we sure we're truly erasing or just making it harder to access? Perhaps the focus should be less on perfect erasure, which might be a regulatory pipe dream, and more on robust mechanisms for controlling access to information and ensuring the behavior associated with unwanted knowledge is suppressed. It's a subtle but important distinction for practical implementation and risk management.
Ooh, that's a fascinating point, Expert 6. Control versus erasure. Definitely food for thought. Let's tackle our last major topic, multi-source memory. This is about handling information from different places and formats. Expert 1.
Exactly, we rarely operate with just one type of information. This breaks down into two key challenges. First, cross-textual integration. How do AI systems reason over information from, say, a structured database, a knowledge graph, and free-form text documents simultaneously? Methods like struct-RAG or ChatDB are exploring this, trying to retrieve and synthesize information coherently. A big subproblem here is handling conflict. What happens when the database says one thing and a text document says another? Identifying these conflicts, like our KCLLM benchmarks, is the first step. Resolving them intelligently is still a major hurdle. Models often exhibit bias towards their internal, parametric knowledge.
Building on what Expert One said, the second challenge is multimodal coordination. Integrating information across text, images, audio, video. This requires fusion, aligning these different data streams into a shared understanding, perhaps in a common embedding space like PaLME or Unitrans CR. It also requires effective cross-modal retrieval. How do you use a text query to find a relevant image or vice versa? Models like CLIP provide a foundation, but extending this to complex, sequential, multimodal contexts like long videos, MALMM, or multi-session chat with images, IGSR, is pushing the boundaries. Aligning these modalities without losing nuance, as Expert One noted for text, is exponentially harder with more modalities.
That's a great analogy, Expert 5. It really highlights the complexity. Now, underpinning all this research is a growing ecosystem of tools. Expert 4, can you give us a quick tour?
Certainly, it's maturing rapidly. We have foundational components like vector databases, FAISS, Pinecone, graph databases, Neo4j, powerful LLMs, GPT, Llama, Claude, and various retrievers. These are the basic building blocks. Then we have frameworks like Llama Index and LangChain, or LangGraph for multi-agent setups, and EasyEdit for parametric modification. These abstract away complexity and provide modular ways to build memory operations into applications. They're democratizing access to these advanced techniques. Above that, specialized memory layer systems are emerging, tools like ZEP, Mem0, or Memabase, offering memory as a managed service, handling persistence, indexing, and lifecycle management. And finally, we see this integrated into products like ChatGPT's memory features, Grok's real-time awareness, personalized assistants like Me.Bot, or enterprise tools like Tencent's IMA, Copilot. It shows memory is moving from a research concept to a core product feature.
And the frameworks piece is key for developers. They make it feasible for teams without deep AI research expertise to start incorporating sophisticated memory mechanisms. It really lowers the barrier to entry.
Absolutely. So, looking ahead, this field is moving at lightning speed. What are the most exciting or daunting open challenges and future directions? Let's do a quick round. Expert 7, start us off.
For me, it's spatiotemporal memory. AI needs to understand not just what happened, but when and where and how things evolve over time. Think logistics, supply chain optimization, or even just remembering a user's changing preferences contextually. Businesses operate in time and space. Our AI needs to as well.
I'm fascinated by brain-inspired models. Concepts like complementary learning systems, fast hippocampus versus slow cortex, memory reconsolidation, or Minsky's K-lines theory about hierarchical memory structures. These offer powerful blueprints for building more robust, adaptive, and efficient AI memory. How do we build AI that organizes knowledge hierarchically like humans do? That's a huge open question.
The holy grail for me is unified memory representation. Right now, parametric, structured, and unstructured memory often live in separate worlds. Developing frameworks that allow seamless interaction, shared indexing, and joint operations across these types would be transformative for consolidation and retrieval.
I'd add multi-agent memory. How do teams of AI agents share knowledge effectively? How do they manage consistency, resolve conflicts, and build collective memory? This is crucial for complex collaborative tasks, but the coordination challenges are significant.
And I have to bring up memory threats and safety. As Expert 4 noted, memory is becoming a core product feature, often storing sensitive data. How do we secure these memory systems against tampering or data poisoning? How reliable is unlearning against sophisticated attacks? As the paper notes, vulnerabilities are being found. With great memory comes great responsibility, and great vulnerability. We need robust security from the ground up.
And maybe a parametric memory retrieval. Can we efficiently query the knowledge implicitly stored within the model parameters itself, without external indexing? If we could ask the weights directly, that could unlock incredible efficiency.
Wow, spatiotemporal context, brain-inspired hierarchies, unified representations, multi-agent collaboration, security, and even querying the model's internal knowledge. It's clear we've only scratched the surface. This has been an incredibly rich discussion. We've gone from the basic types of AI memory and the atomic operations that govern them, through to system-level applications like long-term personalization and handling massive contexts, modifying core knowledge, integrating diverse data sources, and the tools making it happen. A huge thank you to our panel, Expert 1, Expert 2, Expert 3, Expert 4, Expert 5, Expert 6, and Expert 7, for sharing your deep insights and bridging the technical and strategic perspectives so effectively. For our listeners, the key takeaway is that memory is no longer an afterthought in AI. It's a central design principle, driving the next wave of intelligent, adaptive, and truly useful systems. Whether you're a tech leader building these systems or a business leader leveraging them, understanding memory is critical. That's all for this episode of AI Forward. Join us next time as we continue to explore the frontiers of artificial intelligence. Thanks for tuning in. This paper offers a new way to understand memory in artificial intelligence. It introduces a classification system based on how memory is represented. It also defines 6 core operations for managing and using memory. The authors classify memory into 3 main types. Parametric memory is knowledge stored implicitly inside model parameters or weights. Contextual unstructured memory holds explicit information like raw text or images. Contextual structured memory organizes information in formats like knowledge graphs or tables. 4 operations help manage artificial intelligence memory. Consolidation transforms short-term experiences into lasting memory. Indexing organizes memory content for efficient access. Updating modifies stored information based on new data or interactions. Forgetting selectively removes outdated, irrelevant, or harmful memories. 2 operations focus on utilizing memory effectively. Retrieval involves finding and accessing relevant stored information when needed. Compression reduces memory size while preserving essential details for efficiency. This framework connects memory types and operations to major research areas. Long-term memory research focuses on persistent information across multiple interactions. Long-context memory research addresses processing very large amounts of information efficiently. Parametric memory modification studies how to change a model's internal knowledge. Multi-source memory research explores integrating information from different origins and formats. The survey discusses techniques like key-value cache optimization for long context. The key-value cache stores intermediate results to speed up processing. It also covers model editing and unlearning for changing parametric knowledge. Retrieval-augmented generation uses external memory to improve model responses. Retrieval-augmented generation combines finding relevant facts with generating text. The authors highlight several current challenges. Reasoning over dynamic, long-term memory remains difficult. Balancing efficiency and accuracy in long-context models is a key issue. Editing complex knowledge within model parameters needs more research. Integrating diverse multi-source and multimodal information effectively is ongoing work. Multimodal involves different data types like text and images. This unified view helps clarify research on memory in artificial intelligence systems. Future research could explore brain-inspired memory designs. Developing unified representations across memory types is important. Creating safer and more robust memory operations is a critical direction. Advancing lifelong learning and multi-agent memory systems is also key.